Okay, everyone, let me have your attention for a few minutes. We have one more lecture, one more quiz, one more exam, and one more lab this semester. So, any issues with lab 4? Having some issues? Okay, we'll try to. I'll try to finish up early so you can get a chance to work on that. Okay, so we had quiz 4 was due last week. I'll just go over that real fast so everyone's clear on that one. Which of the following is an LTI? LTI is linear time invariant system. This one can't be because you've got two variables that are being divided. This one is two variables being multiplied. This one seems good, right? Just these are linear, so we just have variables that are multiplied by constants. This one is a variable squared, so that's no good, right? So it's the third one. Which of the following is the S-domain form of the derivative of g? It's pretty much just g times s, right? And option 2. Which of the following is a method for determining if an LTI system is stable? Let's see. Check if the order of the denominator polynomial of the transfer function is 2 or less. Nope. That does mean something, but that doesn't tell you if it's stable. Check if the numerator of the transfer function is non-zero. Numerator? No, that's not it. Check if any of the poles of the transfer function are in the left-hand plane, meaning that the real part of the poles is negative. And that would be that one is, actually, if they're all in the left-hand plane, it is stable, right? The last one says check if the impulse response to the transfer function is bounded, which is more correct, right? Basically, this one says if any of the poles are in the left-hand plane, the question is if any of them are not in the left-hand plane. Okay, which of the following are valid eigenfunctions of the transfer function 1 over s squared minus s minus 56? So this one you have to pretty much just do the procedure I showed in class, where you have to get it into a form, this form, which is the sum of two S-domain functions with a constant numerator and the denominator, order 1 polynomial. And then from there, you solve for a and b, and you figure out the eigenfunctions. Okay, any questions about that? Okay, and then what is the transfer function resulting from feeding the function 1 over s plus 1 into the function s over s squared? You just multiply those two guys to figure that out. This one says you're designing a cyber-physical system to counteract the movement of a regular pendulum. You need to model the physical system for the plant, which consists of a hanging pendulum whose angle is theta t. The system input is a force F of t. The time domain equation for the system is f of t plus the second derivative of theta t equals b over m times the first derivative of theta t minus g over L times theta t. So this basically, I just looked this up. This is just the pendulum equation. I just Googled that. That's where that came from. Where m is the mass, b is the friction, L is the length of the pendulum, g is the gravity, F is the force being applied, and theta t is the angular position of the pendulum. Basically, the angle. So straight down would be 0. What's the S-domain transfer function? So to solve this, you have to first get this guy into the S-domain, and then you have to reformulate it so you have it in terms of the output over the input on the left-hand side of the equation. So in this case, the output is theta t, and the input is the force. So the idea is that you're putting this force on it to manipulate theta, the angle of the pendulum. Okay? Okay, so this is the time domain equation. I convert it to S domain by capitalizing letters. Second derivative is s squared. First derivative is s. Constants are constants. And then you have to rearrange it here to get it basically theta. As I mentioned, theta is the output and f is the input. So you want theta over s, f over s to get the transfer function. It'd be really cool to build something like that, right? Like, imagine like there'd be like the pendulum, you pull the pendulum out and let it go, and it goes to swing and it just stops it, right? The electronics stop it cold immediately. That would be cool. I've never even seen anything like that work, but in theory it's possible, right? What is the S-domain transfer function of a PID controller with KP, KD, and KI set as follows? So this one I cheated a little bit because I just put it straight into the S-domain. So the proportional is just basically the constant, right? Just 2, right? Plus the derivative multiplied by s, which is just 1 times s. And the integral term is just multiplied by the integral, which is s to the minus 1. So that's just 4 to the s minus 1. Hey, make sense? And then you can also put it into a standard form by multiplying it by s over s. All right, and then this is the last question. What's the Tustin transform of this transfer function with t equals 1? So Tustin transform is easy. You just substitute s with the Tustin transform term. So in this case, the value you're substituting is 2 over t times z minus 1 over z plus 1. So this is going to take it from the s domain into the z domain, but this is a good segue into the next lecture. Notice that there's a t in here. So it's not just doing a straight s to z. It is incorporating the time step. And depending on your time step, you'll get a different transformation. And in class, we talked about how the z-domain transfer function has a stability criteria, although it's kind of mamby-pamby. But the idea is that depending on how you set the t-value, you may actually end up getting the difference between a stable or an unstable controller. You guys with me? So this basically what I'm saying is that the important aspect of this is t. What's your time step? The idea is that you may be able to design a rocket that lands upright as long as that t is small enough. And the only way to make that t small enough is to have a super powerful computer that can actually perform the necessary control outputs within that time step. And you got to be Elon to do that. Got to have a custom ASIC, right? Otherwise, you can't have a small enough time step. You need a super powerful computer that keeps that time step low enough to achieve a stable transfer function to get the rocket to land. No one else has ever done that in the history of the planet, right? So that's the important. This is really this is the whole reason I cover the Tustin transform, is to introduce this concept of the time step, because then this segues into real-time systems. Okay, right, so you take the S and you substitute it in, then you just refactor everything to get it into the output over input transfer function form. Oh yeah, and what's the closed loop transfer function for the system below? This one's kind of a trick question, because normally when you have a closed loop controller, there's only 2 blocks here, controller and plant. The heck is there 3 here? I don't understand. Why is there 3? Well, it doesn't matter. You can have 3. It's not a big deal. You just convolve. You just multiply those guys. You can create a unified open loop transfer function by multiplying f times g times h. I'm sorry, f times, yeah, that's right. Notice there's no of s there, but there should be. It's f of s. And technically, the transfer function here is f of s over e of s. This is g of s over f of s. This is h of s over g of s. I didn't write that down because it's just an accepted shorthand to show it that way, right? But technically, all 3 of these blocks are transfer functions, and you calculate the open loop transfer function by convolving them, which just means doing a simple algebraic multiplication with all 3. The problem, though, is it's closed loop, not open loop. We want the closed loop transfer function. So to calculate the closed loop transfer function, you simply just take the open loop transfer function and you divide it by 1 plus the open loop transfer function. And this will give you, basically it's going to give you the process variable of the plant, right, which is the feedback here, relative to the set point, right? So the goal is what I want for the closed loop transfer function is to have the form is the state of the plant, which is this feedback connection, the process variable, or say, whatever you're trying to manipulate, whatever you're trying to bend to your will, right? The value of that relative to the set point. And the idea is that we should be able to do anything we want with the set point as long as it's bounded, and the corresponding plant state should also be bounded. So we should have bounded input, bounded output stability. In other words, we should be able to do anything we want with the set point without the plant blowing up. Anything. No limits, right? As long as it's not infinite. As long as we don't get an infinite set point, it should be good. Okay. Yeah, so that's as I mentioned, open loop is FGH, and its closed loop is FGH over 1 plus FGH. Okay, and then finally, what is the discrete time domain implementation of the transfer function 2z plus 3 over z squared plus 3z plus 2? So this one, again, is just a matter of doing some solving. So basically, the issue here is that you can't directly implement this in software. You have to get into a form in which the output f of z is a function of all the variables, inputs and output variables, multiplied only by non-positive exponents of z. You guys with me? Right? Because remember, a positive exponent of z, it means future value, right? Future sample. A negative exponent of z is a past sample, and the current exponent of z is the current sample. So the idea is we want to set the current output as a function of the past inputs and the past outputs, right? So you just have to make sure that all your z exponents are negative. Well, the problem is they're not. I got 2z, right? That's not going to work. So you just have to do some manipulation here. So the way I did it, and it's probably not the easiest way, I multiplied the right-hand side by z to the minus 2 over z to the minus 2, right? So this is just 1, but that takes all of the z exponents to non-positive, right? Right, and then and then I multiplied both sides of the equation by this denominator here, right, to get it out of this ratio form, and then you distribute everything, and then you essentially just end up moving f of z. Why f of z? Why does it have to be f of z? Because that's your output, right? That's your output. F of z is your output. G of z is your input. But you might say, well, wait a minute. I also have f of z's on the side with the inputs. That doesn't make any sense. Well, yeah, that's okay. You can do that. Again, as long as they're multiplied by a negative power of z, this just basically requires you to remember what your past outputs were. If you knew what your output was one time step ago, then you just substitute that in here and multiply it by 3, right? That makes sense. So you're just changing the format. And then once you have it in this form, you can trivially convert it into the time domain, because as I mentioned, the z, negative exponent of z, just refers to how many time steps ago that sample corresponds to. So f of z times z to the negative 1 is simply just f of t minus 1, right? And technically those should be square brackets, not rounded brackets. That's usually in discrete systems use square brackets. Don't know why I use rounded there. Okay, any questions? Okay, great. Next thing I want to talk about real fast is the next lab. So we have another lab due in roughly 2 weeks, I guess, 10 days? 10 days. Not even 2 weeks, because the semester is over soon. But this is not as hard as lab 4. So the hardest lab is lab 4, where you write the low-level driver and have to bit bang stuff. And I thought we would have debugging capability, but we don't. So we're back to square
When
one.
we do, we just have been using.
No, I can't get it to work.
Oh, really?
Launch Arduino, hit debug, and it tells you to go screw yourself. Doesn't work. It says it can't launch DDB.
When you upload it, are you getting debug? Because I got it to work.
Oh, okay. I have never.
We can figure it out next year.
Maybe some of you have gotten it to work. I haven't. Alex got it to work. Has anyone gotten debugging working? Okay. I've never gotten it to work. It does not work for me. But anyway, but that's okay, because in this lab, the same thing happened last semester when we first ran this lab, is we were kind of running out of time. And our plan originally was to write low-level drivers for this lab too, but I was like, we just didn't have enough time. And plus, I think one lab is enough for that. So in this lab, the only low-level driver you have to use is the LEDC driver, which you already have. You already have the LEDC stuff, right? So you're going to take your LEDC code. You can reuse that. Except in the old lab, you were using that to control audio, right? In this lab, you're going to control a motor. So as it turns out, you can control audio and motor with exactly the same kind of signal. That blows my mind, right? I think that's pretty crazy. But the pulse width modulation can control audio, can play a song, and can control the speed of a Tesla. So same peripheral there, but we also need to monitor the motor speed, how fast the motor is turning. And the motors use a quadrature encoder for that, which basically is just a series of pulses. Every time the motor turns 360 degrees, it's going to give you 100 pulses. So if you measure the amount of time it takes to get 100 pulses, then that gives you how long it takes to do one revolution. Does that make sense? Right? So you want to be able to count the pulses. However, counting pulses is beneath software. Software shouldn't have to deal with such a trivial task, right? So you don't want to do any kind of direct software monitoring of that. You want to do that in hardware. And it just so happens that there is a peripheral on the ESP. Well, there was on the old ESP. Hopefully there's one on the new ESP as well, called pcount, that apparently that'll take care of that for you. Like I said, originally we're going to try to talk to the pcount peripheral through control registers, but that one was even more complex than RMT. So for this one, we're just going to use the built-in drivers. The problem is that the Arduino doesn't have any built-in drivers for pcount. Only the Expressif IDF has those. So we're going to use, but that's fine because we can access those too. Additionally, you guys know from the last lab that if you're trying to do two things in your software at one time, it's kind of hard, right? You guys were playing audio and you were controlling the LEDs all from one main loop, right? Which is wildly ad hoc and, it's not fun to do that. So the other thing we're going to do is try to help you with that. We're going to take advantage of free RTOS, which is designed exactly for those kind of tasks where you have multiple things that you want the free RTOS to manage, right? You want free RTOS to time multiplex the CPU, to share the CPU among two tasks, but you don't want to have to manually implement that. This is something that the OS is designed to do, okay? Does it make sense? Everyone with me? Okay, so what is the goal? The goal is to basically make the motor go a certain speed, right? So we just want to implement a closed loop controller. You have the motor. We got motors here that are dangerously powerful for some reason, as Alex learned when he almost broke his finger on it. Yeah, Alex put a second hand on the motor that he 3D printed and almost broke his freaking hand.
Yeah, maybe set a current limit so you don't. I just realized that.
Well, no. What we decided to do instead is not put the... Alex decided that putting the second hand on there was a grievous error. And so we decided just not to give you that. And so now, when the motor spins, it's not actually spinning an arm that can break your finger. It's just spinning a shaft, which I think the only way you can get in trouble is if you try to grab the shaft and squeeze it, right? So we should be okay. All right, so the point is that we want to be able to essentially take control over the motor and make it bend to our will and spin it with a closed loop controller. And you might say, what's the problem with that, man? Just use an open loop controller. Give it a 50% PWM signal, it'll go 50% of the speed. What's the problem? What are you, retarded? Just do that. Well, the problem is that 50% PWM isn't necessarily going to give you 50% of the speed. You may have a nonlinear relationship between the way the PWM period is and the actual speed. So this is why you need to have a closed loop controller for that. You need to actively monitor whatever the speed currently is, and if it's too high or too low relative to your set point, you need to make some adjustments, and so you're going to develop a PID controller for that. Does that make sense? Right? Okay, so that's the idea. So we have two peripherals involved, P count and LEDC. And once again, LEDC is being used for something other than LEDs, which is wildly confusing, but it's just misnamed. LEDC is really a PWM controller. They just call it LEDC to be jerks, right? And the P count is literally for counting pulses, which that actually makes perfect sense because that's how the motor tells you its speed, is it gives you pulses that you count, right? And you determine the rate at which the pulses come in. Okay, so the quadrature encoder basically, as I mentioned, gives you pulses. It gives you two sets of pulses that are identical, which seems redundant. But the reason it does that is because it uses the phase of those two identical signals to communicate to you the direction the motor is spinning. And it turns out these motors can spin clockwise or counterclockwise. The problem is that you might say, well, that's fine, except how do you put a negative value? How do you modulate a negative value on a pulse width modulated carrier signal? You can't, right? So what you have to do is there's a separate output on the motor called direction. So the PWM signal just gives you the speed in one of the two directions, but then you have another output, a binary output that determines whether you're going clockwise or counterclockwise, right? There's also a brake signal going to the motors too, which actually somehow brakes the motor with the tiny brake pads, I guess, that are inside the motor. Unclear how that works, but we don't need it anyway, so it's not a big deal. So you got this counterclockwise and clockwise. Basically, you've got A and B are your two signals, and if A goes high before B goes high, then you're going one direction, and if B goes high before A goes high, you're going the other direction. That's essentially the way it works. In this lab, though, I think we're only going one direction, right?
Yeah.
So in this lab, we only go one direction, so you actually don't have to worry about looking at A and B and measuring the relative phase. You just have to look at either A or B to determine the speed, right? Okay. Now let's see. Yeah. So P count peripheral. So maybe Arduino might have gotten on the ball on this and actually created an Arduino driver for this, but at least as of last year, one did not exist. And so we're using driver/pcount.h, which is part of Expressive, not Arduino, right? Yeah. So the Expressive, the nice man in China wrote this driver for us for the P count peripheral, right? And so you just include it here, and then you create handles for it. You have to have a handle for the P count peripheral itself and a separate handle for the channel, the P count channel, because it's designed to support multiple channels, which would make sense if you had a robot with many degrees of freedom, articulated limbs and such. In this case, we just have 1 degree of freedom, and thus we have one channel. Let's see. So you set it up with another data structure called pcountunit_config.t. So we're already on our third structure, but that's such is life when you use the drivers. And you can set it up like this, and I'll let you guys go through that. You could basically just copy and paste that code. And so when you set it up, you initialize the handle with this pCountNewUnit. You initialize the channel with pCountNewChannel, and then you basically set the edge action. And this basically determines what happens to the P count when you get an edge. So you can program that to increment or decrement. In this case, we're incrementing, so P count channel edge action increase. And then this clears the count whenever you want to clear the count. This enables it, and this starts it. So basically the idea is all this thing does is count. It just counts pulses. And so you can combine this counter with the timer in your code to basically count the number of pulses and divide by the amount of time that you spend counting, and that will give you essentially the RPM, which, well, it's counts per second, which you can change to RPM just by dividing that number by 100 because it's 100 pulses per revolution, right? So that's pretty straightforward. Yeah, and then you can get the count with this function and clear the count with that function. You don't have to clear the count. You can just use a differential. Although I think the reason we have clear count is I think it overflows at like 16,383, right? Yeah. Right. Oh yeah, right. So yeah, so it'll actually so that's why you want to clear count, because you want to watch for overflows. All right, free RTOS. So these chips are actually running an operating system, but it's a real-time operating system, which are not operating systems like you normally think of them. Normally, when you think of an operating system, you think of a prompt, a blinking cursor with a prompt. That's an operating system, something you can type commands into. FreeRTOS does not have a prompt, does not have a shell, does not have any way to interact with it whatsoever, aside from statically linking your code into it and calling functions from it, right? So to use, and that's pretty typical for real-time operating systems. So basically, you include two files, freertos.h and task.h, and then you can create something called tasks. Tasks are just processes, or tasks, things you want to do. In this lab, you create a task for monitoring the motor and another task for running the PID, right? So you can create a task create. So there's this function called, so there's a task handle. This is similar to like a pthread handle, if you guys ever write pthread code in Linux. And then you can create a task with x task create, and then you can give it a handle and a function. Okay, so then you write the function, and that's going to be your task. And the idea is every time that task is called, you execute the task. Now here's the problem though with this. You would expect the way this works is the task would automatically be called by FreeRTOS, right? So you would have the task function, you run your code and you return from the function, right? And then the task gets reinvoked, right? That's what you would expect. Well, that's what I would expect. Maybe you don't expect that. That's what I would expect to happen. But FreeRTOS does not work that way. Once you exit that task, it's done. If you return from the task function, it's over. It's killed. So instead, you have to put an infinite loop inside the task. But the way that you basically create this behavior where the task gets periodically called is by having this vTaskDelayUntil function. So what this function does is when you call vTaskDelayUntil, it's basically like exiting the task, except what it's really doing is putting the task to sleep. So you call vTaskDelayUntil, that puts it to sleep, and it allows FreeRTOS to schedule other tasks on the CPU, right? But it also allows you to basically control how long it sleeps, right? So this is the way that you create this kind of periodic behavior, is that you have an infinite loop, you do what you need to do, and then you tell it to sleep until the next time step, right? That's it. Okay, so we talked about PID controllers, and you guys have experience from this from the robotics class 274, so I'll skip that. Yeah, I mean, the thing about PID controllers that always confuses me is the units. You have these variables, right, like RPM. That's your process variable. And then you have PWM duty cycle. So you're using the RPM to generate, the error. The error is how far off the current RPM is from the RPM you want. And then you're using that to calculate an output from the controller, which is a new duty cycle, right? So that's essentially, that's what you're doing. It's just, it seems weird that the RPM is being used to generate a duty cycle, but that's what's happening there. Okay, any questions about that? Okay, great. Next thing is the last lecture. So I'll try to get through. This one's pretty quick. This is not as long as the control theory lecture. So the next topic is real-time scheduling or real-time systems. And so the issue, have any of you guys heard of a real-time system or real-time operating system? Has that ever come up? Maybe in robotics, they might have mentioned it, right? So the idea is anytime you design any kind of software that interacts with the real-time world, it has to keep pace with the real world, right? The physical world. But the problem is that any modern operating system that you guys are familiar with, like Linux and Windows and iOS, make no guarantees whatsoever about how long it'll take to execute a task. So in iOS, you can't say, hey, I want to run this task, but I really need it to be done in 100 milliseconds. iOS is like, nope, not happening. Guess what? Not happening. I'm not going to make that promise to you because I might just want to have to do other things, right? May have to delay your task longer than you might want me to, right? And so that's why they're not real-time operating systems. Now, Linux recently, they've incorporated some real-time features into later versions of the Linux kernel. But it's still not strictly a hard real-time operating system. If you want that, you're going to pay tens of thousands of dollars a year in licensing fees. That's the going rate for VxWorks and any other real-time operating system. There are no free real-time operating systems except for FreeRTOS, but the distinction there is it doesn't make guarantees, all right, about execution time. So FreeRTOS is really technically not, it's kind of a misnomer. It's not really it's not an RTOS at all. Because what makes an RTOS is it promising you, guaranteeing that you'll meet certain performance constraints, deadlines, latency deadlines, right? So that's a load of crap, FreeRTOS. Can't name it that. That's false advertising. Okay, so right, so I talked about that. Okay, so the real issue, though, is there's a couple problems that you have to resolve. One of them is worst-case execution time. So if you have a task, like, for example, calculating the output of a closed-loop controller, you basically have to have an idea of how long it takes to run that, right? So I mentioned that, basically for some control problems that have very high-rate dynamics involved, for systems that are very stiff, like landing a rocket on a pad. That's a very stiff system. It has very fast dynamics. You have to be able to, you have to have some notion that you can give the rocket a new control instruction fast enough. And that requires you to have this notion of worst case execution time. The problem is it's not really straightforward to actually know the worst case execution time because you have non-determinism. You have sources of non-determinism in a CPU. You've got things like interrupts and cache misses and TLB misses and page faults and other things like that. You also have if statements. Does that make sense? Why would an if statement matter? Because if you have an if statement in your code, the dynamic instruction count that's executed may be different depending on the outcome of the if statement. So any kind of control dependencies in your code at all can change the execution time. Right? Probably shouldn't have a lot of if statements in control code, though. I'm just saying. Probably a good rule of thumb, right? But that will change it. So, so how do people actually measure worst-case execution time? Generally speaking, it can only be done statistically. So one way to do it is to measure the execution time over and over again, and you expect that it's going to vary. The problem is that can you match like a distribution to the variance, the jitter, the execution time jitter? Maybe not. Sometimes. For example, if you assume that it's a normal distribution, then you can calculate the standard deviation. And if you take the mean and you add, say, 3.719 standard deviations, then that will be your worst case execution time with a 99.99% confidence. Make sense? So you take the mean execution time and you add to the mean a certain number of standard deviations, and depending on how many standard deviations you add, you can get a given degree of confidence that that's your worst case execution time. So for example, if you have a task and you've got, say, it runs in 12 milliseconds, 13, 10, 14, 11, 30, 27, 25, 31, and 32, You can calculate, this is what I'll ask you on the exam. You basically just look at these times, you calculate the standard deviation, the mean and the standard deviation of these times. So the mean is 20.5, the standard deviation is 9.2. And if you add 3.09 standard deviations, you can get the 99.9% confidence. So in this case, that's 48.9, right? Now, that looks kind of bizarre to me, right? You're saying that I've got times that are 12 milliseconds and 13. You're telling me the worst case is 48? That's quite a lot compared to what I'm seeing here, right? Right? That kind of sucks. That's awful. That's real, real bad. But as it turns out, the problem is that what ended up happening in this case is I actually had two separate distributions here. Because if you look at 12, 13, 10, and 14, and 11, that's kind of, they're kind of like in one group, right? And 30, 27, 25, 31, 32, it was like in another group, right? So I had a mixture of Gaussians here, right? And you might, why would you have that? Well, because obviously the code was written in a way where there's an if statement. And what you're seeing is basically two different control paths or two different modes, right? Now, is there anything we can do about that? Yeah. If you know that, you can actually give yourself a tighter bound. You can calculate the mean and the standard deviation for both sets of measurements for both groups. And then, if you take the mean plus 3.09 standard deviations of the standard deviation for just the larger group, you know, the higher execution time group, you can actually get a tighter bound. So in this case, I can calculate 38, right? So if I take the mean of just the high numbers, which is 29. So if I just take these guys, 30, 27, 25, 31, 32. So there's 1, 2, 3, 4, 5. If I know that those 5 belong to a separate mode, then I can calculate the mean of those as 29 and the standard deviation of those is 2.9. And I can actually give a tighter bound. I get 38, right? For the worst case execution time. But that's assuming that I know that I have some insight into the behavior of this thing, that I know there's two sort of operating modes. Otherwise, if I group everything into one giant distribution, I get a 48 is my worst case execution time. I get a looser bound. Okay, so that's worst case execution time. But what about actually running these tasks? So I mentioned that free RTOS, the objective of free RTOS is to time multiplex the single core that we can use on the ESP32. So the idea is that you want to be able to run a task and put it to sleep and then run another task. So you're sharing. You've got multiple tasks that are sharing. And this makes sense, right? Because you're probably, if you build a robot that has an arm that has, say, I don't know, how many joints does an arm have?
2 or 3.
Yeah.
Okay, so if you have a robotic arm with, say, 3 degrees of freedom, right? So I can go like this and like this and like this, right? You're probably not going to have a separate controller for each one, right? Probably not, right? You could. It'd be easy. But probably not very economical to buy a separate processor for each output, right? You probably want to have separate one processor that's managing a lot of control loops, right? That's the idea. So like, and oftentimes the time steps for those controllers may not be harmonics of one another. In other words, they may not be multiples of one another, right? You might have a 10 millisecond time step and a 15 millisecond time step and an 11 millisecond time step, right? You have these mixtures of steps, right? So you have to rely on being able to schedule all those things on the CPU without any of them violating their time step, their deadline, without even running longer than their deadline. Does that make sense? All right, so that's called the scheduling. That's the scheduling problem. And so the idea is that you have these tasks, and they can either be ready, meaning that they're ready to be executed, but they're not being executed, which is terrifying, but it just means that the CPU is trying to get something else done first, right? So they're being deferred. So they're ready to run, they're ready to go, they're ready to change the fin on the rocket, but you got to wait because I'm busy, right? The CPU's busy, right? They can also be asleep, meaning that they're not ready to run. They've already run in their current time step is they've manipulated the fin on the rocket, and they're like, all right, we got to wait till the next time step starts before I do anything. So that's asleep, or they can be executing. So there's one of three states they can be in. So let's say you have 4 tasks, and say generally each task will have a deadline, which is how long it has to run, how long the maximum time it has to run from the time that it is ready. Okay, and then there's a worst case execution time, right? That you know the worst case execution time for the task. And so the goal is to figure out, given a set of tasks and their execution time and their deadline, is it possible to satisfy everyone's deadline? Because the scheduler has to make decisions about, who waits to give someone else time on the CPU. But if it goes too aggressive with that, it may cause certain tasks to miss their deadline, to not run in time, right? So I actually, in this case, these are non-periodic tasks. So I assume that they're only ready once, and then once they get done running, they're asleep permanently, right? And so given that there are 4 tasks, there are actually basically 4 factorial orders that you can run them in, assuming that when you start running each one, you run it to completion. So in other words, we're assuming that these are not preemptible, right? You guys with me? So preemptible tasks would mean that a task that's running can be put to sleep and then can be a task that's running can be switched to ready and then back to running before it goes to sleep. In other words, I can take a task that's running and I can interrupt it. And that's preemption. If you look at this case, there's no preemption because it's a simplified view. So there's 24 schedules, because in each schedule is essentially determining the order that I invoke each task, right? And I assume they're all ready at the beginning, right? So anyway, so I created these plots where these plots represent, basically it just shows you which task is running. So you can tell I used I recycled my SPI code for this. So this, obviously, we assume in this case only one task can run at a time. We assume there's only one core, just like on the ESP32, there's only one core. So in this case, you can only run one task at a time, and 1 means it's running, 0 means it's not. So in this case, I run task 4. When that finishes, I run task 3, and then task 2, and then task 1. And I put these little red lines, I don't know how visible these are in the back, but there's these little red lines that represent the deadline of each task. And as it turns out of the 24 different ways to run these guys, every single one, except for, I believe, 2, there's only 2 orders that actually will satisfy the deadlines. So in this case, you can see I ran task 4 first, and that finished on time. Then I ran task 3, and it finished on time, barely. Then I ran task 2, and it finished on time, but it had a very long deadline. And then I ran task 1 last, and this one blew its deadline. Okay? It ran past its deadline. But on this second order, I ran task 4, then task 3, and then I ran task 1 and 2. So basically all I did was I swapped the order of task 1 and 2, and that made everyone happy. That everyone met their deadline. But then I tried it again on that order 3, which is task 4, then task 2, then task 3, then task 1. That actually blew 2 deadlines. We missed the deadline on 3 and on 1 in that case, right? So there's 3 more that all blew their deadlines. There's 2 more that blew the deadline. That number 8 made it. That was task 4. I'm sorry, that was task 3, then task 4, then task 1, then task 2. That was okay. These 3 didn't make it. 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 Okay, so it turns out that was all 24, right? So out of 24, only 2 of them worked, right? So it turns out that if you look at the 2 that worked, actually ended up following a principle, simple principle. Number 8 that worked actually was doing essentially scheduling them in the order as determined by their deadline. Earliest deadline first. So the earliest deadline was task 3, right? It has the leftmost red line, so it was scheduled first. Then task 4 had the next earliest deadline, so I did task 4. And then task 1 had the next deadline, so I scheduled him, and then task 2, right? Number 2 also succeeded. This was task 4, task 3, task 1, task 2. And this one actually was following a principle called least slack first. The slack is just the difference between the deadline and the execution time. That's the slack. So whichever one has the least slack goes first, which happens to be task 4, then task 3, then task 1 and 2. So what I'm really talking about here is priority, essentially. I'm assigning a priority based on, in this case, the earliest deadline, and in this case, the least slack. So the priority priority just means order, like which order, whoever has the highest priority gets scheduled. Whichever of the tasks haven't been run, I choose the one that has the highest priority, right? So again, in this case, the highest priority was the earliest deadline, and this one is the least slack. Sometimes people use something called shortest task first, but that actually doesn't work in this case. So the shortest task is task 2, then task 3, then task 4, then task 1, but that one was garbage. It didn't work. Okay, so the problem is, though, it gets way more complex than that, because in that example I showed, as I mentioned, it is non-preemptive, first of all, but it actually wouldn't make sense to have preempted those guys anyway, because they all started at the same time and they only ran one task, right? In reality, as you guys might imagine from what we're going to do in this lab 5 and what I talked about in terms of the closed loop control, tasks are periodic. So basically every task runs according to its time step. And so the idea is that at the beginning of its time step, it becomes ready, right? And its deadline is simply whatever the time step is, right? So the period, which is how often it needs to be run, is actually equal to the deadline, right? So if I have a task, if I set up my Tustin transform to have a time step of 100 microseconds, that task will run every 100 microseconds and it must run and complete within 100 microseconds, right? So that is the most common use case for a real-time scheduler, is this idea of a periodic scheduling, right? So in that case, each task will have a worst-case execution time, but also not a deadline, but a period, right? So the problem comes into the play here, because this period may not be, as I mentioned, they may not be harmonics. They may not be multiples of one another. Check this out. I've got a period of 76, 84, 35, and 37. So the periods don't align in any way, right? So that's the issue. So one of the problems you have to solve, and this turns out to be a really hard problem. In fact, it's unsolved. This is an open problem in computer science. No one knows how to solve this. The question is, what is the schedulability test? How do I test this requirement to determine if it is physically possible to schedule these guys without blowing any deadlines? Is that possible to do? Well, sort of. There are schedulability tests out there, but all they do is tell you for sure if something can be scheduled. But no schedulability test will tell you that for sure something can't be scheduled unless it requires more than 100% utilization. So let me talk about that for a second. So utilization is going to be, if you sum up the execution time divided by the period for each one of these tasks, that's going to give you the utilization for the schedule, right? So 40 over 76 plus 6 over 84 plus 14 over 35 plus 20 over 37 will give you utilization. If that utilization is more than 100%, then obviously it's not feasible to schedule it, because you can't do it on not on one processor anyway, right? You can't do it on one processor. Or in general, if you have n processors, if the utilization is more than n times 100%, you're not going to be able to schedule it, right? So that's easy to figure out, right? The problem is that if the utilization is under 100%, even then is it possible to schedule it, right? Well, that depends on the scheduling algorithm that you choose. That depends on how you set your priorities. Okay, so one of the ways to do it is to use earliest deadline first, and I mentioned this in the context of the non-periodic one. So earliest deadline first basically says, whenever I make a scheduling decision, I will schedule the task with the earliest deadline first. The problem with that, and that might seem pretty straightforward. I mean, a lot of you guys use earliest deadline first when you're deciding what project to work on, right? The problem is that earliest deadline first requires you to calculate priorities after every task is ready. Whenever any task is ready to run, anytime a new period of any task begins, and whenever any task ends execution. So does that make sense? You guys with me? So in other words, the priorities, the priority is based on the earliest deadline, which is basically, in order to figure out the earliest deadline, you have to know what the current time is, and you have to figure out where the next period ends relative to the current time. You guys with me? Right? So you have to recalculate priorities on every task end and on every period begin. And it turns out that is not practical. It takes too long for the scheduler to do that, especially if you have a lot of tasks. It's not practical to do earliest deadline first. But earliest deadline first, it turns out, will always work. It will always be schedulable as long as your utilization is less than or equal to 100%, right? But it's not practical because, again, if you have a task period that starts, another task may be already running, in which case you have to put it to sleep and switch to another task. There's a lot of switching you have to do, right? And a lot of recalculating priorities. A much more common approach is rate monotonic scheduling, which is where you set basically whatever has the shortest period as the highest priority. And thus, you never have to recalculate priorities as a function of what the current time is, right? Anytime a task becomes ready, if it has the shortest period of all the ready and running tasks, you just run that one, right? It's very simple. In other words, the priority is not a function of the current time. The priority is a function of only the periods and not of whatever time it currently is. So here's an example of earliest deadline first. So here's a set of 3 tasks, 1, 2, and 3. You've got the time, the period. This ends up having a utilization of 80%. That's 10 over 40 plus 15 over 50 plus 5 over 20. So that's 80%. So you would think, that's cool. I mean, that's 80%. That should work. With earliest deadline first, it does work. So here's the 3 tasks. And now I've marked red lines that show where each period begins, right? So the deadline is you have to run each task between each pair of these red lines. That's the period start and end, right? Does it work out? Yeah, it works. No one violates their period, right? It works out. In rate monotonic scheduling, on the other hand, I did the same thing with rate monotonic, and did this one work? I think this one worked too. Yeah, this one was okay too. Right? Now, one of the things you'll notice, by the way, when you look at this is check out these periods. They're all weird relative to one another, right? Because their phases are all over the place, right? They start and end at arbitrary times relative to one another, right? You also notice here, task 2, for instance, was preempted here. You see task 2? Task 2 started here and it ended here. It ran for a little bit, but then task 3 took over. Task 3's period started here and it preempted task 2. But luckily, task 3 finished pretty fast, and I was able to go back to task 2. You see this preemption here? So this shows that task 2 ran twice, but not because it was invoked twice. It ran once, and then it got put to sleep, and then it got to finish. Right? It makes sense? Okay, so so here's another example. This one has a utilization of 98.3, and this is where the EDF schedule succeeded, and the RMS schedule failed because we missed the we missed the deadline. Now this also shows, you might say like, well, if you want to know if something is schedulable, why not just simulate the schedule? Like you did it right here. You generated the schedule. You found out this guy wasn't schedulable because it missed the deadline. So what's the problem with that? Why not just simulate the schedule? Well, you don't know how long you'd have to simulate it for, right? This guy didn't bust a deadline until way out to here, right? You may simulate something for a long time and you don't have any violations, but if you had just run it for a little longer, simulated it for a little longer, there could have been a violation. So simulation generally is not sufficient. What you want is a mathematical way to determine this. So here's the RMS schedulability test. When I was in grad school, there was a different one for this, believe it or not. When I was in grad school, we were told that two guys named Liu and Leyland wrote a paper in the 90s that proposed the schedulability test for RMS schedules. And they created what was famously known as the Liu and Leyland bound, which basically said that for RMS scheduling, as long as you were less than 69% utilization, it was guaranteed to be schedulable. If your utilization was greater than 69%, maybe, but no guarantees, right? But since then, since the time I was in grad school, there has been a new bound developed for the RMS. So now, instead of it just being a percentage, they have a test where you take each of the execution times in each of the periods, add 1 to each of those ratios, and multiply them all together. And if the result of that is less than or equal to 2, then it's guaranteed to work. So this is a tighter bound than the original Liu and Leyland bound. Still not perfect though, because if you violate that bound, it still may be possible to schedule it, but it's a risk because you don't know. Makes sense? And by the way, what I'm talking about is, I'm talking about the region between where this bound ends and the 100% utilization hits you, which you know after 100% utilization, there's no way you can schedule it, right? Make sense? Okay, so essentially here it's just 10 over 40 plus 1 times 15 over 50 plus 1 times 5 over 20 plus 1. This schedule has a 1.95. That's less than 2, so this one's good. This one, same thing, except that it says 2.33, so this one fails, right? So this is just a mathematical bound that says if you're under that bound, if you meet that bound, you're guaranteed to be schedulable with RMS on one processor for a given set of tasks. Okay. Now, it turns out that RMS does have this special thing where it will schedule up to 100% utilization if the periods are mutually harmonic, meaning if they're multiples of one another. So that one works. Okay, and then last thing I want to talk about is multiprocessor scaling. So what if you have more than one processor? Can you do real-time scheduling? You can, but it's even harder. There's 2 ways you can do it. You can use partitioned scheduling, which is where you just assign, you have a set of tasks and you assign certain tasks to one processor and certain tasks to other processor, like if you have 2. Or if you have more than 2 processors, you basically just assign, you take your task set and you decompose it into groups that are associated with each processor, and then you just do single processor scheduling, right? Problem solved, right? That's easy, right? The problem is that how do you make those groups? Well, that's up to you, right? That's on you as a designer. On the other hand, you could use a thing called global scheduling, which is where you allow the scheduler to put any task onto any processor. That's better, right? That would be better if you could do that. Then you wouldn't have to worry about assigning tasks to processors. And there's several algorithms for doing that, none of which I think this is still an open problem. One of the basic ones is called rate monotonic first fit periodic scheduling. And the idea with this one is that it's like a greedy algorithm where you basically assign a task to the first processor that passes the single CPU RMS schedulability test with the other tasks assigned to it. So in this case, you're basically locking in each task to a specific processor, but you have the scheduler do it at the beginning, right? Does that make sense? So this is kind of like partition scheduling, except it's automatically partitioned, essentially. And then this one has a schedulability test associated with it where basically you just calculate the utilization. And if that utilization is less than or equal to m times the square root of 2 minus 1, then it meets it. So the square root of 2 is 1.41. If you subtract 1, it's 0.41. So basically, if m is the number of CPUs, you multiply that by 0.41, and that is the highest utilization you can have and be able to guarantee schedulability with this algorithm. You guys with me? In other words, you can only use 41% of each CPU. That's not great, right? So basically, in this case, if you have 4 tasks, these are the tasks right there. The single RMS schedulability test, remember, is 1 plus 2 17ths times 1 plus 2 19ths times 1 plus 5 21st times 1 plus 7 23rds. You multiply those together and you get 1.9949. So that's good, right? That's less than 2. So that would actually work on 1 CPU, right? On 2 CPUs, you apply this other test where instead of multiplying together 1 plus, the individual utilizations, you just calculate the overall utilization. So you add up, that's 2 over 17 plus 2 over 19 plus 5 over 21 plus 7 over 23. That gives you 76.5, which on 2 CPUs, you have to be less than 0.82, right? Because it's 0.41 times m. So 76.5 is less than 82%, right? But just barely. So it barely works on 2 CPUs when we knew it actually would even work on 1.
What would be the buffer in between the utilization and the 2 CPUs?
The buffer?
Yeah.
Oh, you mean like the difference?
Yeah.
Well, it's like for 2 CPUs, it's basically you get like you can get up to 82%. With 1 CPU, I don't know actually. I'd have to. That's a good question. I'm not sure how it works out because it's not based on utilization. It's based on adding and multiplying together 1 plus the individual utilizations. So that's a good question. I don't know off the top of my head. Right. Okay. So there's another example. Skip that. Okay. And then finally, the only other global scheduling algorithm that I know of is called is earliest deadline first global scheduling. And the idea is again, this one is based on dynamic priorities. So you have to determine what you're going to schedule based on the priorities that change every time a task begins or ends. So essentially you schedule, you go through and you figure out who's ready. So at the beginning, all 5 tasks are ready. I'm going to do T3 first because it has the earliest deadline because it has a period of 10. T5 has a period of 15, so I'm going to do him second, right? Now, the T5 actually, even though it had lower priority than T1, it finished earlier. It finished first. So now after T5 finishes, that's when I have to make a decision of who to schedule next. At this point, the only ready tasks are 1, 2, and 4, right? Because 5 is done and 3 is good, is running, right? So I only have 3 tasks. So of these 3, I have to pick which one has the earliest deadline, and that would be T2. And then when T3 finishes, I only have 2 tasks that are ready, T1 and T4. So I pick which one of those has the earliest deadline, which is T1. And then again, after T1 finishes, I'm sorry, it didn't finish actually. It didn't finish. What happened is who's red? T3 became ready, right? So T1 actually didn't finish, but I still had to make a decision because this red guy, was ready to go, right? So I probably have to preempt T1, right? So I reran T3. When do I pick T1 up again? Check it out. So T1 gets another chance to run, but here's the thing. The soonest it gets a chance to run is actually on CPU 2. So T1 actually had to migrate from CPU 1 to 2, right? But that's okay. We assume we can do that. And then so on and so forth. So yeah, so basically, that's the way global EDF scheduling works, right? So how good is that? Well, that one, it turns out, remember I mentioned that EDF scheduling will schedule on one processor as long as utilization is less than or equal to 100%. Global multiprocessor EDF scheduling, that's not the case. So in that case, the way you do it is the utilization obviously has to be less than M, where M is the number of CPUs. But even if that's true, you basically just calculate the greatest common divisor of all the periods. Greatest common divisor of all the periods, right? Which is what? Looks like 5. 5 is the greatest common divisor. And then you multiply that by the ratio of each. And you guys with me? So basically it's 5 times 24 over 40, 5 times 8 over 20, 5 times 4 over 12, 5 times 16 over 40, and 5 times 3 over 16. If all of those values are integers, then it's schedulable. I mean, it's guaranteed to be schedulable. I mean, it may still be schedulable if not, but there's no guarantee. Make sense? So that's kind of an esoteric test, but that's the test. Okay? Okay, that's all I have for this lecture. So final exam will be this material plus the control theory stuff plus the stuff from the first half of the semester. We'll have one more quiz, which I'll post when I get back to my office. I'll make it due at the end of next week, so give you guys enough time to take it. And then lab 4 is due today. Lab 5 will be due essentially the last day of the semester, which is the 24th, 10 days from now. Okay? All right, thank you.